Hi everyone, welcome back to the tutorial video for Pchem exam. And the second portion that I want to talk about is about the Raoult's law, more detailed about Raoult's law, as well as phase changes and phase diagrams, as well as, if we can get all the way through, the lever rule as well. So let's look at the Raoult's law for now, and just kind of, I think most Pchem material focus on Raoult's law a lot, so I'm kind of spending a little bit more time on that as well. So you've already learned and derived from the previous video the Raoult's law, that is the partial pressure of A is equal to the pure vapor pressure of A times the mole fractions of A. Now, the confusions and the complication happens when you have a gas phase and a liquid phase, and both in the gas and the liquid you have some moles of A and B, some mole fractions of A, mole fractions of B, as well as a partial pressure of A and partial pressure of B. So you have A and B materials are both vaporizing and dissolving inside the solution both at the same time. Now, the equation for the partial pressure of B, it remains the same. This partial pressure B is the partial pressure of B when it's pure times the mole fraction of B. Now, so far so good. And majority of the time what we want to know is not just the partial pressure of A and B on its own, but rather also the P total. And this P total is just the additions of PA and PB. So it's just, we're just going to add these two things together. So partial pressure of A plus pressure of B is equal to the total. But the partial pressure of A and B can be written as the pure vapor pressure of A times the mole fraction of A plus the pure vapor pressure of B times the mole fraction of B. Now, we still have too many variables because now we have mole fractions A and B. We have to make it a bit simpler. Now, if my solution only contains molecules of A and B, then I know for sure that the mole fraction of A times plus the mole fraction of B must be equal to 100%. That is, if my solution contains 30% A, then in order to get to 100%, it must also contain 70% of B. So essentially, if you have one information, you should be able to get the other as well. Specifically, we're going to solve it for mole fraction of B is equal to 1 minus mole fraction of A. And the reason why I want to write it down in terms of B is I'm going to substitute that in there. To rewrite it, that P total is equals to partial pressure of A star times mole fraction of A plus partial pressure of B times 1 minus mole fractions of A. And if I were to simplify this even further, this will be PA star minus PB star times mole fraction of A plus PB star. So this is P total. Alright, so what would the graph look like when we combine the partial pressure of A, partial pressure of B, as well as the P total all in the same graph? Alright, so the graph would look something like this. So we have, in this case, 0% B, and then 100% B. And this is the mole fractions of B. Okay, so we're going to rewrite it with respect to, actually let's rewrite it with respect to mole fraction of A. And let's make another assumption. Suppose that I know that the molecule A is harder to boil, such that the partial pressure of A is less than the partial pressure of B. So think of A to be water and B to be acetone. So B vaporizes easily. So PA star is of A, or the pure vapor pressure of A is less than that of B. So if we have 100% of A, then my vapor pressure would just be the vapor pressure of A star. Right? So if I have 100% A, this is going to be PA star. If I have 0% A, then that means I have also 100% of B. So the partial pressure is, or the total pressure is PB star. Okay. So let's try to draw the Raoult's law in this case. So the Raoult's law is just linear from one to the other, so it's just a linear graph. So this one is partial pressure of B, and then I'm going to use the green color to denote the partial pressure of A, and again it's just going to be linear. This is partial pressure of A. Now the total pressure is just the summations of the two, so the total pressure is just A plus B. So we have that line here. This is P total. Sorry, it's curving a little bit. We're going to make it a little bit straighter. So this is P total, which is just PA plus PB. Okay, so this is the graph that you've seen in your textbook as well. But that's not all we want to stop in. You see, when you vaporize the material, it so happens you'll find that the vapor pressure is not going to be the same. That is, I'm trying to get to is that the mole fractions in the gas phase and the mole fractions in the liquid phase is not going to be the same, because one of the liquid is easier to vaporize than the other. So in the gas phase, you'll have more of the gas of one kind than the other. So they're just simply not the same thing. And your book uses a new variable called y, and y is defined excuse me, as the mole fraction in the gas phase. And that is in contrast to x, which is the mole fraction in the liquid phase. Okay. So how do we calculate from y using the equation that we've done so far? So y, if I were to look at the mole fractions of A in the gas phase, so y of A, this is equals to the partial pressure of A divided by P total. Now if I were to do that, we can rewrite this as PA is just Raoult's law, PA star times mole fraction of A in the liquid phase divided by the P total, which we've already derived as well, is going to be PA star minus PB star times mole fraction of A plus PB star. Okay, so this is mole fraction of A. So how does this graph of y look like in our Raoult's law pressure versus mole fraction diagram? I'm going to erase the individual component here. So I'm just going to write down the P total. So the first line here is the P total. This will give you the one of them, and I'm going to draw y of A on the bottom here. I should probably change one of the colors as well. Okay, so I'm going to use y of A as the red line. So, and then I'm going to use the black line here as the mole fractions in the liquid phase. Mole fraction of A is going to be the black line there. All right, so this is what we have for now. And we're going to have, I just want to make sure really quick, hold on. Yep. That the black one here is the liquid composition. And then the red line here is the gas composition. Gas composition. That is to say, if I were to have my liquid, right, so that's a gas composition and or Y, and then the black one is the liquid composition or X. So this is 0% A and 100%, let's use a different color again. So I just want to clean up the graph a bit, 0% A and 100% A. So suppose that I have a solution. So suppose that I have a solution containing 90% A, right? So I have the liquid composition is 90%. So I have chi or X is equals to 90% A. So it's going to be somewhere here. So that's my 90% A. X is equal to 90% A. What I will find is that in the liquid phase, that the vapor composition is going to be different. Because again, A is harder to boil. This is PA star. This is PB star. So A is harder to boil. The vapor pressure is less than that of B. So what happens is that you will have the composition of B is going to be higher in that regard. So while your liquid composition is 90% A, you may find that your gas composition is going to be different. That is, this is about the 50% Y. That while your container contains 90% A by mole, the vapor phase contains 50% A and then 50% of B. So it's just saying that your vapor and liquid composition is not the same thing. Okay, so that's kind of the basics for it. That the main issue is that the liquid composition and the gas composition is not going to be the same because the partial pressure, one of the liquid is going to be easier to boil than the other. So you'll have, in any concentration, the vapor pressure of the one that is easier to boil is going to dominate the partial pressure. You're going to have a bigger contribution from the molecule that's easier to boil. Okay, so that's just kind of the graph for now. This is where I'm going to jump and leap a leap of faith a bit, because your textbook doesn't actually go through it in greater detail. It's actually kind of hard to derive. And what they did is they kind of take a leap of faith and say, okay, suppose that I were to look at this not as a pressure and mole fraction diagram. Instead, I'm going to look at it as a temperature and mole fraction diagram. My graph is going to look more or less something like this. That is, I have, remember, A is harder to boil, so the boiling point of A is higher compared to B. So this is boiling point of A, and this is boiling point of B. And what they found is that, so suppose that this is the graph for A. So this is my liquid composition. The vapor composition is going to look like this. Oh, sorry, yeah, vapor. So this is mole fractions of A. What I'm doing here is it's a bit of a leap of faith, and your book didn't derive it. But this graph here, the first pressure versus mole fraction graph, can be converted to temperature versus mole fraction graph, and it looks more or less like that. And when you're doing distillation, this is the one that you want to know. And the idea remains the same too. So that is, if I were to have, say, a 90% solutions of A, so this is 90% A, what I will find is that the vapor composition is not going to be 90% either. I will find, because A is harder to boil compared to liquid B, that the composition in the vapor phase is going to be different. That is, even though my solution containing 90% A, my vapor pressure may only contain, in this case, about 55% A or something like that. Right. So it's just, they're just different. The vapor compositions and the liquid compositions are different. Now, let's go into, let's take this ideal case and learn a bit more about distillation. So I'm jumping the gun between one to the other. We're just going to talk about the ideal case for now, and then we'll make correction to real gases and so on. Or sorry, real solutions and so on. So how does distillation work? So if you've taken OChem before, you've done distillation, so the setup looks something like this. You have a reflux setup, and then you have a condenser, and then you let the condenser drip into a container, right? So how does this work? So suppose that I have a 90% A solution, and I want to distill B. Okay. I want to get rid of this impurity of A. So what can I do? Well, I can boil it at whatever boiling point that I have here. So it's going to be a higher boiling point. And then I'm going to have the vapor. So I have the solutions. I make sure that it boils nicely and on a hot on a heating mantle. So the vapor is going to evaporate. But you'll find that the vapor composition is not the same as the composition of A. So even though the solution contains 90% A, the vapor will contain, in this case, as I'm drawing here, only 55% of A. So if I were to then condense this vapor into a liquid, then my new distilled liquid will contain a 55% solutions of A. Right? So I change my liquid into a vapor, and this at the boiling point, whatever that is. And as I condense the vapor back into a liquid, my composition is changing now. Okay. And my new liquid composition will be at 55%. Now, how about if we want to kind of continue making a purification of this thing? Well, what we have to do is we take the same liquid, the liquid that we distilled, and we set it up to another distillation setup. So now we have a 55% solution. Put it into a distillation chamber, and then condense it out. So what is the new concentrations of this new distillate if we do the distillation process twice? Okay, so now we have to boil this liquid again. So I have this liquid with this particular composition, in this case 55%. And I'm going to boil it again. So I'm going to convert it from liquid into gas. So this is the vapor composition. So that's the vapor line. Okay. And now if I were to convert it to gas, my gas composition is going to be somewhere here. What is this? About 33%. And as I condense it back, my new solution would be 33%. So now the liquid that I distilled will be 33% A. And I can keep going. So essentially what the distillation or the boiling point diagram look like is that if I have a 90% solution of A and I want to get to 90%, I would have to do 1, 2, so first step of distillation, I have to do 2 steps of distillation to get 33%. If I want to go to all the way to, say, what is this, 5%, I would have to do the 3rd step. Now you can see that as it gets closer to the end here, you would have to do a lot of distillations, but your purity doesn't change that much. And that's kind of why some of the liquids that you see in the laboratory is much more expensive than others. So you can get from Home Depot a big jug of acetone that's 90% pure for, you know, $10. But if you were to get the same, so let's say you can get a 90% pure of acetone for about $10. That's because in order to get to 90%, you kind of just have to do 2 types of distillation. But if we have to use a laboratory grade, which is 99.999% acetone, you kind of have to do 3, 4, 5, 6, 7, 8, 9, 10. You can have, you know, 8 step of distillation. So that's why the prices of this guy is going to be, you know, it could be $200 or something like that. Just because the distillation step happens multiple times, it's harder to do because there's just so many steps involved. And as you get purer and purer and so on, the price goes up, 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 and up. Now that's the distillation, and how to use this distillation, figure out the distillation graph. And what you're doing is essentially just kind of making a step. If you have this amount of solution initially, a percentage in solution, then in order to get to this point, you have to do 1, 2 step of distillations and so on, or 3 step if you want to go to this point, and however many that you do. Okay, let's kind of move on to another case where the case is non-ideal. And non-ideal case is just non-ideal, so there's an infinitely many way that a solution can be non-ideal. So I'm just going to choose one, and specifically I'm going to choose an azeotrope in this case. So suppose that I have an azeotrope that looks like this. So remember, if you're remember whenever you're looking pressure versus mole fraction diagram, the gas composition is on the bottom and the liquid is on the top. But when you're looking at the temperature and mole fraction, these two things are switched around. I'm going to use the same color now. And just remember that the the gas phase is going to be the top. Let's make it a bit more pronounced. Okay, so this is the vapor composition, and the black line is going to be the liquid composition. So what is, before I go over there, the azeotrope is essentially a location here. This is the azeotrope where the liquid and vapor composition is the same. And usually it can either be a positive high like this, or you can also have an azeotrope that looks in reverse. That is, you can have an azeotrope that looks downward. Yeah. So you have, for example, you have an ideal case that always looks like this. You can either go up or you can go down. Either way, there's a lot of different kinds. Now, how does the azeotrope going to change with respect to everything else? Your book specifically doesn't derive how, doesn't even explain how azeotrope happens, but what I want you to know is just they're just non-ideal. And similar to non-ideal gas, a non-ideal solutions is that you have in the liquid phase A and B starting to interact. Either they make the bond tighter or they make the bond looser, whatever, and that contribution is going to provide to you an azeotrope one way or the other. Not always, but some azeotrope can have it. So let's kind of look at this azeotrope in the case of distillation as well. How is it going to be different or the same for the distillation case of the ideal solution? So let's say I have a solution, so this is my 50%, 100% A, and 0% A. This is 25, this is 75. So let's say we start out with, a 10% solution at, say, 298 Kelvin. So let's say we have a 10% solution of A at 298 Kelvin. What do I need to do to get distillation out of it? Well, what I would need to do is increase the temperature so it boils. So now all I'm going to do is I'm just going to boil my liquid from the liquid phase to gas phase here. And then I'm going to do distillation, and I'm going to repeat the step several times. Now what happens is that if you have an azeotrope, you can see that I can't go beyond this point anymore. There's no more ladder step because the liquid and vapor composition is the same. So the maximum purity that I can get from, if there is an azeotrope and I start out here, then the maximum purity that I can get is only about 55%. Right. That's just where if this is my progression, is I'm going the arrow this way, that's as pure as I can get in terms of my azeotrope. Now if you're starting here and go that way, it's fine. If you go that way, it's also fine. So I can go this way and go to 100%. but it's somewhat directional. Your purity in this case, if you start from 10% A, you can only get all the way to 55% A, at least based on this graph, because of the presence of the azeotrope where the liquid and vapor composition is exactly the same. So you can't distill it any purer than this. All right. So